before starting about binary star seismology, I'm just going to sum up single star seismology. So astroseismology is a way of peering inside stars. It comes straight from helioseismology, so I'm going to start with that actually. From helioseismology, and so the study of the waves inside the sun, we got these solar-like pulsators that are, if you can see my cursor here, at the bottom of the main sequence here, and they include solar-like giants, red giants, stars here. So low mass star or very big stars. The other kind of pulsators we call classical pulsators. Those are the upper main sequence in a very broad meaning, going from gamma Dor stars that are, well, the progenitor, the prototype of that class is Gamma Doradus, and these stars are around 1.3 to 1.6 solar masses, up to tenths of solar masses along the main sequence. But classical pulsators also include compact pulsators. So in this plot here, you have the SDB, SDO, subdwarfs, B and O stars. The DAV, DBV are white dwarfs. I'm not going to make the difference between these two kinds of white dwarfs. They share a common excitation mechanism, almost all of those classes. That's why they're packed together. In all these stars, you have two main kinds of waves. Gravity modes that are not gravitational waves, obviously, they're buoyancy modes. And you have pressure modes that are simply sound waves, acoustic waves. On the plot on the left, some of the, well, the direction of the strikes through the domains here show which kind of wave you have where. So solar-like, and this inclination here for the lines means P modes. The other inclination, like in SPB stars or DBV stars, means gravity modes. I'm going to use G and P modes. Those are gravity and pressure modes. Well, please keep that HR diagram in mind. I'm not going to show it again, but I'm going to refer to these classes. So solar-like pulsators, they're obviously similar to the sun. They have modes that are excited stochastically from convection. Basically, convection is putting energy in the whole range of frequencies it can cover, and the modes that survive, the waves that are selected, are the ones that create a stationary wave throughout the star. The ones that interfere destructively, you don't see in the spectrum. So these include main sequence stars, subgiants, red giants, as I said. To analyze those, you have three easy steps. Well, they were not easy at first, but now they're well understood, and I like to say they're easy. So the three steps are mode identification. To each frequency in your spectrum, you want to associate a geometry for the mode, and we can do that. You have regular patterns in spectra, and you can use inversion techniques. So I'm going to explain all of this. Mode identification, it's pretty easy if your star is not a fast rotator or doesn't have an extreme magnetic field that breaks symmetry and include more and imply more complexity, obviously. In that case where it's simple, we have spherical harmonics to describe the modes. Each mode is one unique combination of a spherical harmonic and a radial sine wave. So you end up having three quantum numbers, N, L, and M. N is the radial order, the number of nodes along the radial line. L is the number of nodal lines at the surface. And M is the number of those nodal lines that are meridians, that go through the poles. Obviously, M is smaller than, in absolute value, smaller than L, or equal to L. And yeah. If you don't have rotation, you have a degeneracy in M. If you have a slow rotation, basically your modes that have the same M, same L, but a slightly different M, they will just split and make a multiplet of modes. We understand that very well. I said there were regular patterns in spectra. Well, these two plots here are the spectrum of the sun. The left one is what you actually measure. So the gray line is Gulf. The other ones are a tool called SPM. not sure which one it is. Well, basically, you have here this peak. This peak is due to granulation. We understand very well how this frequency here, where it peaks, is linked. To stellar properties. On the other hand, when you zoom on this plot, you find what you have on the right. What you have on the right here is the spectrum of the sun still zoomed in, and you can identify each peak. And we identified the peaks that have L equals 0, 1, 2, 3 here. And what you're supposed to see is that they make this cone that is nicely spaced, regularly spaced. From this, you derive this quantity here, delta nu. That's the distance between two peaks with the same L and consecutive ends, so consecutive radial orders, but the same number of nodal lines. In this case, radial modes. This delta nu is called the large separation. Nu max is called frequency at maximum amplitude or something like that. And basically, both of them are related to the mean density of the star or granulation properties, and from that you can derive mass and radii with some percent precision. With enough frequencies, you can use inversion techniques. Inversion techniques are basically the evolved version of this. You can compute what we call kernels. These are the propagation domains of the mode inside the star. And when you add or subtract modes from each other, you can basically find kernels that zoom in a very specific part of the star. So here, for instance, your modes 2,1 and 2,2, if you subtract 2,1 from 2,2, you end up having a very nicely, a kernel that is nicely concentrated along the equator. If you added them, you would have something averaged more or less throughout the star. But if you use K31, then suddenly you can zoom at mid-latitudes and so on. Doing that, you can have much better resolution on what happens inside the star. All these plots I'm showing are meridional cuts, by the way. On these plots here, also the plot of the sun. I'll go back to it. This is the rotation profile inside the sun. It's a meridional cut. Near the rotation axis, we don't have any information because the modes we measure don't probe there. Everywhere else in the sun, we have a very nicely detailed view. These four parts here near the rotation axis, the slightly faster areas within the radiative zone, those may be spurious. So let's go back to later. Okay, did it freeze?
Oh no.
I feel like it may. I can't move slowly.
Video is still working though.
Oh, the video is fine.
Yeah,
I think it's the laptop. It's rejected you.
Am I dumb? That dumb or?
No, something is wrong. Yeah. I think you need to use yours.
I need to use mine. Okay.
We do. This is the artistic pause.
Thank you. Is it recording? Yeah. Okay.
Yeah.
So guys, let's go back. So you may remember from a previous talk how solar-like pulsators work. Okay. So basically, the three steps I wanted to highlight with my previous presentation, that was meant to be a standalone one, obviously, are these: mode identification, regular patterns, and inversion techniques. These are for solar-like pulsators. There are some very interesting results that were obtained from this. We were able to do statistics, basically, so separate between red giants and clump stars for a sample of 16,000 stars from Kepler, to compute core-to-surface rotation ratios increasing, sorry for the typo, with age for subgiants. So basically, we see that in subgiants, the core accelerates and the envelope spins down while the star goes through the Ashburn gap. We were able to compute core-to-surface rotation ratios. That's about 20. So the core rotates 20 times faster than the envelope for red giants. get some insight, not really solve, but get some insight into the lithium discrepancy in 16 Cygnus that are two stars that are very similar to each other, and they're kind of solid twins. Also galactic chronology and archaeology, that's the big thing Andrea is doing in Brum. And finally, get in-depth analysis of solid twins. I didn't put a reference because there are many and I wouldn't know which one to pick. I don't want to hurt anyone. Okay, so that is for solar light pulsators. Now classical pulsators, they have this other excitation mechanism that I mentioned quickly. It's called the kappa mechanism, at least for most of them. It's related to an opacity layer, creating some kind of valve mechanism near the surface of the star. The gamma door stars also have this, they have this convective blocking mechanism that I've never really fully understood, so sorry about that. Here on the right, you have an example of, I forgot the reference, it's Handler 2019. It's a runaway star that happens to be a beta SEP star. So it's a kappa mechanism of the iron peak that excites the oscillations. And well, you have here the process of pulling out frequencies. So you take the most obvious ones, you remove them from the spectrum, and you start again until you only have noise left. So in this star, we identified 38 frequencies. And maybe it's not obvious with this plot, but trust me, they don't really follow any kind of pattern here. Mode identification is not obvious because we don't know the wave selection mechanism in these stars. We know the excitation one, but we don't really know why some of those modes would be visible and some others would not. So basically the three-step method I described before doesn't work here. But we still have interesting results. Here is one case for gamma door stars. So each one of these plots shows the same thing. These are three trends for different modes. If you take these, for instance, the top left one here, these are L equals 1, M equals -1 modes. And you take the frequencies of these modes for consecutive ends. And you see this kind of wiggles that are tilted with some kind of slope. The slope increases when the rotation rate of the star increases for all the panels. The difference between the first, the second, and the third column is the order, the azimuthal order M of the mode. So the modes in the middle are zonal modes. They don't have any meridian nodal line. The ones on the left are retrograde. The ones on the right are prograde. And the difference between the top row and the bottom row is diffusion. In the top row, there is no diffusion in the model. In the bottom row, there is some. And what you see is that the wiggles are caused by basically glitches in the structure, or at least discontinuities in the structure that are smoothed out with diffusion. So those wiggles tend to disappear. If you increase the diffusion even further, you have straight lines, basically. And the slope in the plots is directly related to the rotation rate of the star, as I mentioned already, in both cases. It's not that obvious for this plot here, but there's still some kind of link there.
So by diffusion, could that also be rotational mixing or something like that? Some other kind of mixing?
Well, yes. In those models, if these are from the code used in Liège, I don't remember the name, maybe Liège. Yeah, the rotational mixing would be treated as diffusion. Okay, so this is for gamma door stars. For delta Scuti stars, I had to talk about those to put my name on at least one slide here. Well, we were able to find some regular patterns. It's not obvious. You have to select a subsample of the modes you predict from the models and compare that to another subsample of the modes you actually observe. But if you, well, we have a strong method to identify those modes. And if you take those specific modes, you retrieve a scaling relation that is in the bottom left corner here. And the observed one matches the modeled one, or conversely. So on the left, you have the first paper with the observations of those stars. Notice that the color bar is for the rotation rate, and you basically have all kinds of rotation velocities for those stars. While on the right, I can't really go through all the details, but basically the gray dots are the observations from the 2017 paper mentioned on the left. So there are more points. The orange and blue points are models with varying core abundances and rotation rates. Basically, this scaling relation is independent from rotation and links simply mean density to that large separation we're able to find. So far, we were not able to find an equivalent to the new max that we have for solar-like pulsators. So we only have half of the package here, basically. Then SPB stars, beta SEP stars, they usually have few modes. So they're not really good for any pattern-like analysis, but they're good for direct modeling. On the left here, you have the observed spectrum of HD 120, well, HD 129929. I didn't put the phone number there. But, the dashed lines, the gray dashed lines, actually are not independent frequencies. They're aliases of the rotation rate of the star, while the black dotted points are the actual frequency. So this star has 6 modes that are clumped in an L2 triplet, an L1, well, we see part of an L1, sorry, an L2, we see part of an L2 quintuplet, part of an L1 triplet, and one L equals 0 mode. And the right part here is the stability study from Dupré et al. The reference got munched by the thing. Basically here, you have the horizontal lines are the observed frequencies. The dotted or full lines that are kind of wiggly are the modes you compute, varying the age of the star. And when it's a dotted line, it means the mode is not excited. A full line, a solid line means they're excited. And basically what you want to do is match the slanted solid lines with the horizontal solid lines, your modeled excited modes with the observed frequencies. And that happens for these two models. They have different masses, as you may see in the corner here, different overshooting parameters, different metallicities, and you find slightly different ages. So the point I make is that the age is pretty safe for the star, while the mass, they actually add some extra information to pick 9.54 rather than 9.21. Now let's talk about binary stars. So one thing that has been discovered, recently dug into, is the pulsational binaries. They're the equivalent of the spectroscopic binaries, except that instead of seeing 2 chemical spectra, you see 2 oscillation spectra. And this is a very nice example where you see that the red peaks and the blue peaks belong to 2 different stars that have a mass ratio of 0.94. These are, if I'm not mistaken, solar-like pulsators, but I don't remember if they're main sequence or not. In this case, the spectra can be disentangled basically by looking for patterns. You can find that you have 2 patterns that are slightly different. If you look in detail here, from this peak here where blue and red are overlapping to that peak here where blue and red are again overlapping, actually blue went through, well, has 1 more peak in the middle. So you have this kind of moire effect. Thanks to that, we can disentangle the spectra and find masses and radii for each star, as you would do if you only had 1 spectrum, basically. Then another thing that helps us constrain the orbits and therefore the stars is the radial velocity method. You simply see the Doppler shift of the 2 stars rotating around each other. This specific case is actually a triple system. That's why you have huge error bars on the blue line. It's actually the center of mass of that smaller binary that you are constraining here. And then you have pulsation timing. So here you have some kind of synergy between the pulsations and the orbit, because what you get is, well, you have time delays in your pulsation due to the distance, the changing distance of the stars with respect to you. And this time delay you can actually measure. It's the y-axis on the bottom plot here. And you can identify which star has which frequency from that, because not all the frequencies, or not all the, only part of the sign of the signal of the light curve is shifted one way, while the other part is shifted the other way.
Mhm.
So you can actually disentangle that, and you get this kind of curves. From this, you can get both the orbit properties and obviously do the seismology. And if they're not classical pulsators, well, or it's tricky. Well, if they're classical pulsators, and you need to know a lot to constrain them from seismology. But I'll come back to this. Last but not least, eclipsing pulsating binaries. Those are very good astrophysical benchmarks. From the eclipses, you can get the orbit, the radius ratios. From the pulsations, you can derive the mass, the individual masses, and the radii. So here is an example. So the red line here on the left is the trend. It's basically what you would get with no pulsations, and the spread of that line is both noise and pulsations. So you can find the orbital period, and you have this spectrum here on the right. You know that you're going to find LESs of the orbital period, but you can remove them from what you know through the eclipse, and you're left with this spectrum here. The bottom plot here is the distribution in terms of orbital period and in terms of contactness in the binary for Kepler data. So they found something like 2,700 eclipsing binaries. So you have slices of 10%. So 10% of those have a period that is less than a third of a day, so 8 hours, and so on until several years. And well, D is for detached binaries, SD for semi-detached, so they're transferring mass. OC is over contact, or as Rob would say, contact. And elliptic binaries are.
Everyone says except for this.
And apparently gold.
And Wikipedia.
You can write any old shit on Wikipedia. Wikipedia is the thing that had the giant penis for the Roche-Loeb overflow, so, you know.
My point here is that these binaries are touching each other. So, for solar-like pulsators in binaries, if you consider two main sequence solar-like pulsators in a binary, it's quite tricky. They're not easy to identify from the PB method, simply because as soon as the mass ratio is not close to one of the two stars is going to dominate, and you're going to measure only that star's pulsations, and you're completely going to screen the other star's pulsations. When I mean not close to 1, like 0.9 is already too much of a mass ratio, too little of a mass ratio to find PB2 stars. You can't use pulsation timing because the excitation is convection, so the modes you excite are not coherent on a time scale that is comparable to the orbital timescale, to period, and because of that, you can't do pulsation timing over one or several orbits. For red giant binaries, it's slightly different. For instance, you can use eclipsing binaries quite easily, and they help us test the scaling relations. You basically have two kinds of systems. The first ones are the closed binaries, short period, there's tidal locking, and tidal locking damps the oscillations, if you trust this paper by Go. Wider binaries, you would not expect a strong tidal effect, but they still show departures from scaling relations. That seems to imply that scaling relations are precise, but not accurate. And that was kind of expected because the physics behind scaling relations is really simple. So yeah, you expected some more complexity to show up at some point. So several improvements have been suggested using different solar values in the scaling relations, adding a linear term to the scaling relations, including a mean molecular weight term in the equations in the relations. These are leads that have been highlighted by these papers here.
Can I ask a question you might know the answer?
Mm-hmm.
You say tidal locking damps oscillations. Does it also prevent the energy damping that tides normally would cause the orbit to, for example, circularize or synchronize?
Well, if your orbit is locked and not circular.
No, I'm not saying it's less. No, assuming it's eccentric, it's not locked.
Okay.
Would there be an effect on the rate of change of the eccentricity, for example?
If it's not locked, yeah, your tidal lag is going to create some torque, basically, that is going to change the eccentricity.
Yeah, because there are many observations of eccentric binaries, which are in systems that you would presume to have locked but haven't. And I wonder if there's something we're missing in there.
I think the point here is simply, just like when you have tidal locking, you don't have significant tidal effects. You just have this constant distortion of the star, and that's it. You wouldn't create the kind of, I don't know, shear that creates the waves inside the star, because you're not shearing anymore, you're just locked. I think that's the case behind that. Okay, so that's for solar-like pulsators. Now let's move on to classical pulsators. You may have guessed that my disclaimer at the beginning was that basically I do classical pulsators. So gamma door stars, there is no pulsation timing possible either, still owing to the excitation mechanism. That convective blocking thing still relies on convection somehow, and you don't have coherent excitation over time long enough. But we can detect these stars as PB2s quite easily because the gamma door range is tiny, so you can't have an excessive mass ratio with two gamma doors in the same system. Also, in a binary system, you would expect stars to have the same age and the same metallicity. And if you use that for your direct modeling, it helps a lot. Here is an example of a system that was computed by McKenna Schmidt. The plots are small, I'm sorry. But basically, these two squares here are the observed values for the luminosity and TF for both stars. And you have evolutionary tracks and models here, light blue and dark blue, linked together. And these are basically the two models that are equally convincing. The difference between the tracks is, I think, the overshooting parameter. And here you have the equivalent for the seismic part of it, where they compare the period separation for the modes in both stars. Here on the left, you have the spectra basically distributed in the two stars. So red are for the primary star, blue are for the secondary star, and the shade shows the azimuthal order. And well, by matching these, both the things in the usual HR diagram and in this seismic thing, you basically can get a satisfactory model that you can trust. This thing here is for a detached binary. I'd really like to work on this or something like that and try to increase a bit the complexity to see what happens if you consider some history of mass transfer or something in there, and see if binaries can help with that. Delta Scuti stars, they're the best candidates for pulsation timing. There are quite a few of them. Most of them are detected as PB1, so there is only one pulsating star, at least one star that pulsates in P modes, one Delta Scuti in the system. The other one is usually a low mass companion. You also have 24 of them that are PB2s, so they're in a system where both stars pulsate. And you also have 150 eclipsing binaries, both from the ground and from Kepler. These eclipsing binaries, they revealed that short period binaries in that range of mass that goes from 1.6 to 2.4 solar masses, you find that close binaries have some history of mass transfer. Otherwise, you can't really explain what's happening there. And delta Scuti stars also often are fast rotators. Surprisingly, the short period binaries are usually slow rotators. But anyway, for delta Scuti stars, we have good observations. There's complex physics. Some people are finding new ways of analyzing them, and I'm proud of being part of that people. So I'm telling you, delta Scutis are the next big thing. I may be wrong, but I hope they are. Next, compact objects. I didn't mention them really before because I don't know much about them. So I did my research for this review and researched the binary ones mostly. So we know for sure that stars that have a mass less than half the mass of the Sun have to be the result of binary interactions. They couldn't be compact objects considering the age of the universe. So that's a pretty strong cutoff. So you have two kinds of star in there. ELM, so extremely low mass white dwarfs. They're the very tiny bump here on the left. The bump is tiny for one reason, is that there are many detections that have been revealed to be false by asteroseismology. That is, you measure a very big log G, so you think it's a compact object, you derive a mass that is around 0.2, and when you do the seismology of those stars, you find out the mass is actually higher than that, and you have some inclination effect or something that screwed you up before. So in the end, you're left with, I think, 5 of them that are safe detections that are confirmed by asteroseismology. And these 5 stars have some RV signals. So they're necessarily at least binaries. Then you have the SDB, SDO stars. Often SDO stars are mixed with SDBs. Like we kind of forget the spectral type. They're subdwarfs with oscillations. The origin is either a merger or a mass transfer. It can't be otherwise, but it's still hard to tell which one it is. It may depend also on the mass or the kind of oscillations you have. Most of these stars are in circular systems, and the tides have been ruled out by Holly, Priest, as the cause for this circularization. Also, the whole seismology arsenal works here, not like the team, and well, you could do something can be done here. I mean, these would be obvious targets if we knew more of binary interactions in the asteroseismology community, I guess. Let's move on. Other compact objects, you have white dwarfs. The orbit studies of white dwarfs are not great, but asteroseismology can help confirm the log Gs we measure, and therefore the masses and the radii. There is much more to it, but sadly I don't know much more. And then with a companion, you can do the weird stuff. So I put this thing here, the Thorne-Jutko objects. I forgot the dot on top of that Z. Basically, it's a neutron star that has accreted an H envelope, and that looks a lot like a red giant, like really a lot. And to the point that we don't really know when we find some kind of weird red giant, if it's just a weird red giant or if it's such a thing. And I guess this could be identified with seismology. I think I have the tools to do that. I don't think I have the time to do it, but maybe someone would be interested in helping.
Yes.
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 Okay.
That would be cool.
We need models of them.
But so, I mean, are there candidates that you already have that you go this?
Personally, no, but well, I think I've heard of something around here.
As far as I know, the only star is CHV2112.
Okay.
There's another one as well. There was a paper out recently, and I forget who by, but you'll find it on Astrogate. There are many about.
But if you have something in asteroseismology, then there's a very
Well, I think no
There's
one.
an immediate test you can do with the abundances, right? Because you get all sorts of weird. You get a very hot burning layer at the bottom of the pH envelope, so you should get a very distinct chemical pattern. And now,
Do you really?
well, this was how HV2112 was found, but then
I saw it. Don't
Well,
worry. Well,
allegedly.
what I mean.
But I agree with you.
At this point, I have. Well, basically, I have studied. I'm mentioning this just in 2 slides. For my PhD, I've been using tools that I think would be suitable for this, whether you want to include a neutron star in the middle or not. Like the envelope would be quite easy to model, provided you know what the boundary conditions are. And that seems to be the trickier part, obviously. But I think I have the tools to compute the oscillations in that fluid, given the boundary conditions you may want to set. I don't think anyone has done that. And to reply to Warwick, who asked through the chat what the TZO oscillation frequencies
You've
would
got a
be,
private chat with Warwick going on.
it's there.
Where
I
is
have
it? Oh, there.
no clue at all. But I'd be
It's
happy
private 'cause I'm
to.
looking the wrong way.
I'd be happy to investigate this.
So also, I thought that the TZOs, because you have, I mean, it's more like a red superdome, right, than a giant, and then you have massive convective stuff going on that just wipes out any asteroseismology you could do. I mean, if that's not the case, that would be super cool.
Well, we can still build a model where it's not the case.
The other question is, I mean, how many red things are there with decent data that you can do asteroseismology on? Because, I mean, TZOs are rare, right? I don't know whether it's...
That's not entirely true. And there's an estimate from Philip Podzyglowski in the 90s, I think, and he reckons about 1 in 10 red supergiants could be a TZO. It's quite a lot, but it depends very much on very uncertain ground.
Yeah.
So, but it could be.
But it could be 1 in 1,000. Or
Could be.
I mean, 1 in 10 just sounds...
Sounds a lot.
Sounds
Yeah.
It's a 1 in 12.
So yeah, how many stars are there with these? Like, would this be Kepler?
Well, I'm much more on the modeling side, and basically what I wanted to do with this is kind of spark the conversation we're having.
Warwick said there's more stuff. So
Warwick just said that. Well, I mentioned this, but Kepler has found oscillations in thousands of red giants, super giants, or I'm not sure. Maybe,
yeah, that's the problem. They would be red supergiants.
Maybe Warwick knows.
They would be extremely bright, and that's the problem. I don't know whether Kepler has seen that many.
Kepler has left aside the very bright stars, but to be bright, you have to be intrinsically bright and not too far away. So I wouldn't be surprised that there were, if we're talking 1 in 10 or even 1 in 100 supergiant. Well, anyway, there's probably something there. Honestly, I would need to know more, to read more, to know about the observing side of it. I think the models would not be too hard to do. I think they were kind of left aside because we don't have solid observations. So you have a lot of people in the modeling community that are just like, why model them if they may not even exist?
I guess if you found something and you find 1 star out of 10 or 1 star out of 100 or whatever, some weird spectrum, you're like a skeptical reader is just going to go, eh. But then if you also have some weird abundances in there, then...
The problem with the abundances in HV2112 is there are other ways to explain them.
Oh yeah, and I mean they're not that weird.
And they're not that weird. That's right.
I mean that's you look at 20 stars and 10 elements in each, and you find one that's a 2.5 sigma outlier.
I guess that estimate you just mentioned, we could compute like an updated one with binary C.
There are papers. We did that in the 2014 paper.
At
least the birth rate we have
there. Read it. So what do you? Or maybe and I didn't.
And the birth rate of them is a factor of 10 or so less than red supergiants, but it's not that small.
Okay.
But then you have the lifetime,
lifetime,
and you
okay.
don't know if the lifetime is the same as a normal ring supergiant. It could be longer, it could be shorter.
We can't compute that with binaries.
The lifetime?
What would you have to do to?
You need detailed stellar evolution models, which we don't have. But I'm hoping to get someone to do that next year.
Okay.
That's
Okay.
write the application.
Yeah, well, I'd be happy to hear more about that.
But actually, that you can think you can do asteroseismology on it is an even better way to sell it. So I'm glad you said that. Really cool.
I think Chris's new PhD student is on the way going to be working on the
Apparently so. Well, he hasn't told me. So.
Anyway, I think these TZOs, to wrap it up, are kind of untapped potential. It's an interesting object, at least if you, well, it's interesting as a physics question. Then is it relevant to astronomy? That's a whole other question, I guess.
Well, the nuclear guys upstairs love them.
I know.
Because there's a lot of RP process, nucleosynthesis, that probably happens at the base of the envelope. So for them, it's the ideal laboratory. And they're actually starting measuring the cross sections now for those reactions. So it's a good way to test it.
Okay. Well, that's it for weird stuff. Now, the last point I wanted to make is about tides and modes. So obviously, when you have tides, you have tidally excited oscillations. They're excited by tidal forcing. So basically, your tidal torque creates some shear that creates the oscillations. The frequencies of those oscillations are multiple of the orbital frequency. They're usually G modes. And obviously, most of these modes are expected to be damped, and that would create more dissipation. I'm not sure about this thing here. Forget about that. The properties of these gravity modes, there's still a lot to be done, mostly because asteroseismology has kind of been driven by pressure modes and mixed modes. So gravity modes that can't be observed in solar-like oscillators, they're kind of left behind. I have a small video that I wanted to show, so I hope I can share this with you. So, no, I don't want to join a meeting anymore. Oh, what did I do? How do I unshare my screen? So I can't go. Oh yeah. No, stop sharing. It's here. Okay. Let me share. So this video I wanted to show you. Here we go. So that's the kind of stuff I have done during my PhD. It's not the published version, so the caption is a bit wonky. Disregard this eta quantity here. N2 is the Brunt-Weisler frequency throughout the, that's the stratification of the envelope. It's also related to the differential rotation. Here I'm gonna vary the Ekman numbers, the viscosity, of the fluid in the star. And what I want to, I'm going to make it tend towards astrophysical values. And what I wanted to show here is that mode, its damping rate goes down when the viscosity goes down, obviously, but it stays, it's still damped, basically. And it concentrates along this kind of structures here. I'm gonna pause it, yeah. Well, these kind of structures inside the star are the shear layers that appear when you have tidal forcing. These the modes that are tidally forced, usually, well, most of them, they excite this layer here that is tangent to the core of the star, and then create this kind of structures here. They're single structures, so they're dissipating a lot of energy. And this dissipation, I was able to quantify here. This is for a mode that is actually not tidally forced, but for excited by rotation. It's a gravitational inertial mode in a rotating shell. And they're very similar to tidally forced modes. The point I want to make here is that with this tool that I've used, we can compute tidally forced modes. and the important part is that they are usually damped. So they dissipate energy in those modes, knowing which ones are excited by tidal forcing and knowing their damping rate at low viscosities will help, well, would help us estimate how much energy is dissipated by the tidal force oscillations. So to go back to the slideshow, that I have to reopen. Each other.
Can you imagine?
Somebody sneezing?
Barely. Okay, so this was for gravity modes. Just to say, there's a lot more that we can do to assess their dissipation. And finally, an interesting thing that only appears in binary systems are heartbeat stars. It's typically a symbiotic example of binarity and asteroseismology, because you have this modulation that looks a lot like a heartbeat, hence the name. This modulation is due to the star getting close. Well, the stars getting closer. So you have this peak in the relative flux due to the pedestrian passage of the star. And this thing you can basically use to constrain the orbital properties of your system, eccentricity mostly. And once you detrend that, well, you have bona fide pulsations that you can analyze to derive the mass and the radii and so on. So these are also a bit like eclipsing binaries. They're very interesting systems that combine seismology and duplicity. So that's it for my review, just a small advertisement for a wonderful workshop that I've been organizing at the end of the month of March.
You fixed the acronym.
Yeah, I fixed the acronym, so I'm going for pulsation of intermediate mass, massive and multiple stars. It's the PIMP's #1 workshop. I just plan on numbering them in increasing order. So we have support from the areas, from the department, from Andrea. Thank you very much, Andrea. And we applied to some more funding from the university. The answer will be given to us in Christmas. But whatever happens with that, the workshop is going to happen. What we can do with the extra funding is basically help early career researchers come to visit us. So that's it. Thank you for your attention here and elsewhere.